This is ECE 341. This will be the fourth lecture, part one. What I'd like to do today is continue our discussion of axiomatic probability. We'll start with a theorem. I think in the book this is labeled as Theorem 1.9, so let's go ahead and label it just that same way. And what this theorem states is the following, that if I have an event space, and we know an event space is just a partition of our sample space, right? And so this event space, we're going to go ahead and label it as B1 all the way through some Bn. So I've got n sets that are mutually exclusive and partition our sample space. And I also have, let's say, some event, call it A. Well, then we can say, we would say the probability of A can be determined as a summation running across all n of those objects of the probability A intersect our Bi. If you remember, our event space, it partitions our sample space. And so if I take A intersect Bi, I should be able to build up A using all the little pieces that are each common to the different pieces of Bi, all of which are mutually exclusive. I can get the overall probability of A by adding up each of those mutually exclusive pieces probabilities. Let's go ahead and see if we can use this. We'll pick a pretty simple example, but it should help demonstrate the utility of this guy. I'm going to look at a couple of event spaces for this particular example. It's going to be related to cell phone communication. So we know that almost everybody nowadays has a cell phone, and usually those cell phones end up getting data to or from by either having a Wi-Fi signal, right? So we can have a Wi-Fi data, or we can use cellular data. So most phones allow both of those. I'm going to just designate that Wi-Fi data as W, and I'm going to call that cellular data as C. Those are the two modes that are going to be available on these phones. And if you think about it, that idea of W and C, that is an event space, right? It does partition all the kind of communications that I would do with my cell phone, and it classifies them based on how we're getting that data on and off the phone, either using a Wi-Fi network or a cellular data network. We could also think about the calls themselves, or the way, the kind of information we're doing. We could think of having a voice call, the reason we used to have phones to begin with, right? And we could also think about something that's more data oriented. So you're sending pictures or video or whatever the case may be. So people use their phones for different things. It seems like voice calls are becoming less popular, and all the other stuff is a lot more popular in this particular case. So you could think of voice and maybe non-voice. Anything that is non-voice would be considered data. This also forms an event space. I'm going to call this V and D, just so I can refer to these in a little bit simpler way. And I'm going to go ahead and note that V and D also form an event space. So I've got two event spaces in here. I'm going to go ahead and assign a couple known probabilities, and then we're going to work with those known probabilities and see if we can find some remaining probabilities. So let's go ahead and do the following. Let's say that the probability of us using Wi-Fi, right, as our mechanism of getting data on and off the phone is going to be equal to 70%. So I'm going to do this as 0.70. Furthermore, we're going to do something along the lines that what's the probability of having a data transmission as opposed to a voice transmission. Let's go ahead and let that be 80%. So 80% of the time we're just doing data, 20% of the time you'd expect that to be voice. This Wi-Fi network is going to be 70% of the time, so the majority of the time we're on the Wi-Fi networks as well. What I would like to do is I'd like to find all the different kind of probabilities that can be associated with this particular pair of event spaces. I think to help me out in this, I'm going to utilize a diagram. This is a technique that I think we should really be making high use of in this class. Anytime you can take what's given, right, and you can get some sort of picture going along, that picture helps us manage the data and can help us with the calculations. So I'm going to go ahead and draw something that's a bit Venn diagrammy. So I'm going to have a rectangle here, and that's going to represent all the different kind of calls that I can do on this phone, and that's whether they're voice or data, and whether they're Wi-Fi or cellular. I'm going to go ahead and show these event spaces, these partitions as well. So I'm going to go ahead and just put a vertical strip in here, and I'm going to let the stuff on the left be all the voice calls, right? And all the stuff on the right be all the data calls, something along those lines. And then if I want to think about the network, I can go ahead and partition going along the other side, something along those lines. And so I'm going to have Wi-Fi as being the top part, right? And cellular being the bottom part. And in this way, we can see the different kinds of combinations that we might be interested in. We might have a Wi-Fi voice call, or we might have a cellular data call, or whatever the case may be. So there's a bunch of different call types in here, and we would like to get a handle on the likelihood of each one of those. I'm probably going to need just one more piece of data in here. So I'm going to go ahead and just give one additional data point in here. I'm going to say that the probability of having a Wi-Fi data call, so something along those lines, is going to be about 65% of the time. So a Wi-Fi data call is being 65% of the time. Now I'd like to find all the other kind of possibilities as far as probabilities that could be associated with this. One of the first things I might note, right, is this idea of a Wi-Fi signal, right? That Wi-Fi signal is anything that is in this upper part up here, something along these lines. We already knew that. We already said that the probability of a Wi-Fi signal was 70%. So I'm going to go over here and just write that out. 0.70% has to be reflected in those two boxes, really, that are bounded in red. We also can do something along the lines of looking at the data signal. I'm going to do that in a slightly different color, so let's go ahead and make that guy green. So if we are in the data part of our group, right, where you've got two boxes again, so we either have a data call that is on the Wi-Fi network, or we have a data call that's on the cellular network, and we said something about that guy as having a total probability of 80%. So those two boxes there have to give me a sum total of 80%, something along those lines. And then the last little bit I had in here was that the likelihood of having a Wi-Fi data call was 65%. So I'm going to go ahead and write that in there. The Wi-Fi data call is the upper right little rectangle there. So I know I have 65. So I'm just going to use this kind of chart, this table that I'm making, as a way of managing the probabilities here. And then on the side, I'm going to go ahead and use that Theorem 1.9 that we just derived to do a more analytic calculation to support finding the other parts of this table. Okay, so what kind of things could we be interested in? I could be interested in what's the probability of having a voice call on the Wi-Fi network, right? So I could ask, what is the probability that I have, if I can get my iPad to cooperate here, a voice call on the Wi-Fi network, right? Something along those lines. One way we can get this is again through Theorem 1.9. And what do we know on this? In this particular case, I'm going to look at the event space between voice and data, right? And I know that we can get this overall probability of the Wi-Fi signal, right? By looking at the Wi-Fi plus voice and the Wi-Fi and data, right? That's just looking at the intersections across that event space. So I get something like this. The probability of a Wi-Fi signal, right, is equal to the probability of Wi-Fi intersected with, if we go across there on top, that's voice, right, plus the probability of Wi-Fi and data, something along those lines. Voice and data form our event space, right? So the intersections of these with the thing I want, right, can be added up together as probabilities to give me the overall probability of the Wi-Fi signal. Well, we had already known that the probability of the Wi-Fi signal was 70%, and we knew that the probability of a Wi-Fi data signal was 65%, right? And so the only thing that we need to find in there is the probability of the Wi-Fi voice signal, and now we have a simple algebraic expression, and we should be able to get from that, right, the probability of the Wi-Fi voice is 70% minus 65%, or 0.055%. I'm going to go ahead and put that in here, and I can put that in 0.05. And what I notice, right, is that if I go ahead and I take those two numbers, 5% and 65%, I do get that 70%. So this graphic here is just a great way of managing the data. In the same sort of way, if I wanted to find the probability of a cellular data call, we could probably look at that chart and recognize that it's going to have to be something plus 65 being equal to 80, right? And so that's going to be 15. We can still do it with that theorem, right? So that theorem says something like the probability Whoops, let's make this into a little bit just regular thing. Probability of a data signal, right, equals the probability of data intersected with each of the pieces that make up an event space, right? And when I look at that data, the event space that I'm going to be looking across is Wi-Fi and cellular. So I'm going to get probability of data in Wi-Fi plus the probability of data and cellular, something along those lines. We'd already computed out the probability of data as being 85% or 80%. So 0.8 is going to be on the left side there. And data and Wi-Fi we had already had filled out in this particular thing. That was our 65, so 0.65. And then I add to that the probability of a data and a cellular. And we go ahead and solve that guy. The probability of data cellular then is 80 minus 65, or 15%, 0.15 as a probability. So I can go ahead and put that in there as well. So 0.15. A couple of other things that we can notice in here. If we know that a Wi-Fi signal takes up 70%, anything that's not Wi-Fi, right? Cellular is all those things that aren't Wi-Fi. You could think of cellular as being what? That is just Wi-Fi complement, if you will, right? It's everything that wasn't Wi-Fi. And we know that something plus its complement has to give us the total probability of 1, right? And so that tells me that this Wi-Fi complement has to be 30%. Let me just go ahead and put that in there, because 30% plus 70%, if I add those guys together, right, I'm going to get a value of 1. That total probability, that's the probability of S, everything in there, something along those lines. In the same sort of way, if I wanted the probability of voice, I know voice is just equal to data complement, right? In this particular case, you're either voice or data. So if data was 80%, data complement is 20%, and data complement is just a different way of saying voice. So I'm going to have 0.20 here as well. From this, I could get that last box sitting there pretty easy. I know that whatever is in that box, let's go ahead and sketch that in blue, that last final one. This is something about like the likelihood of having a voice on the cellular network call, right? I could get that by looking at that vertical column. 5% plus whatever's in that blue box has to be 20%, so that would suggest 0.15. I could have also gotten it across the row, right? The 30% chance of having a cellular call is going to be the cellular data at 15% plus the whatever voice cellular is, which is again going to be 15%. So if I go ahead and put that in there, I did mental math calculation, 0.15 in there. That 15 and 15 going across the row there does give me the 30% as I'd expect, and the 5 and the 15 gives me the 20 on the column as I expect. Everything's adding up. So if I wanted to come back down here and do that last one, the probability in this particular case of a cellular voice call, how could we get that? Well, one way we could get it is just by the law of total, kind of the total probability of all these pieces. We have 2 event spaces in here, and we know that their intersections, right, must all add together. So there's 2 things in the first event space, 2 things in the second event space. And if I take all their intersections, that gives me a total of 4 things. Those 4 things cover all possibilities in my example, and they are going to have to add to 1. So I know that the probability of S, which is 1, right, is the probability of having, for example, a Wi-Fi voice plus the probability of having a Wi-Fi data plus the probability of having a cellular voice plus the probability of having a cellular data. Now, before I had done that blue thing, right, which was the cellular voice, we ended up having the Wi-Fi voice, we had the Wi-Fi data, and we had the cellular data. Now, if we went ahead and plugged in all of those pieces, Wi-Fi voice, right, was 5%. So we know that this is 0.05. Wi-Fi data was was that, I think, 65, right? 0.65. The other one over here was a 0.15, and we were just adding in probability of CV going into this, and they all have to sum up to 1. Do that, and again, we can get this just by direct calculation, as we would kind of hope. So charts can help, graphs can help, but really in the end, that math is probably the most proper way to do this. That probability CV is going to be 1 minus 0.65 minus 0.05 minus 0.15, which equals 0.15. I'm going to clean that up just a tiny bit. So 15% probability as we got. So a couple things on this particular example. We use this example to just better look at this theorem 1.9, which tells us something about computing out the probability of an arbitrary event A using some event space, B1 through Bm. We just basically add up the intersection of A with all those event space pieces, the BIs. And then we also took a look at just, again, this advantage of using some sort of graphical method to help us manage the data. Let's move to a different topic at this point. This topic here is pretty interesting. It's in many respects very similar to what we've already covered in just basic probabilities, but it's basic probabilities with a kick. We're going to add some prior knowledge and see how that affects the likelihood of different events going on. This all falls under what is called conditional probability. So let me go ahead and write that out. What is called conditional probability. So we're going to go ahead and look at conditional probabilities. Whoops, did not spell that right, so let's get that corrected as well. Probabilities, right? So we're going to look at this idea of a conditional probability. And basically what this says is it says that prior knowledge, right? Prior knowledge can affect, probably should do that as an affect, that would be more appropriate. So it can affect the probabilities of an experiment. Before I get into this in a mathematically kind of defined way, let's just think about a simple exercise and think about how prior knowledge could affect us. Let's consider an example where I roll a six-sided die. So go ahead and roll this six-sided die. This is one that we've already taken a look at. We'll let it be a fair six-sided die, and we know that that universe then is what? It's numbers 1, 2, 3, 4, 5, 6. If every single one of those is equally likely, if the die is fair, the probability of I is just 1/6. That's also one that we took. That's I equaling 1 up all the way through 6, something along those lines. So that's just a regular old die roll. Suppose I roll a die and I ask you what's the probability of a 1. I think you'd be totally justified at that point saying, yeah, the probability of a 1 being rolled is 1/6. Okay, so that's just the normal experiment, and it's its normal probability that we'd expect. If I rolled that die and I hid it from you, I hid it from you with my hand though, right? And I told you, I said, I rolled an odd number. What's the probability that it was a 1, right? I've given you some additional information about the outcome of that experiment without actually telling you what the outcome of the experiment it is. I told you that I did not roll an even number. I told you I rolled an odd number. So if I came in here and I thought about all the things that couldn't have happened, when I said that it was odd, a 2 couldn't have happened, a 4 couldn't have happened, and a 6 couldn't happen. And that means there's one of 3 things left over, and I would have expected that the probability of a 1 now went from a 6th, right, to a 3rd, something along those lines. This is that idea that prior information or extra information, right, can help adjust or modify the probabilities of interest. So now in this case, I'm saying what's the probability, right, that I equals 1 given, so I'm going to do that with a straight line, that the roll outcome was an odd number, right? And we saw in that case that it was 1 out of 3 because there's only 3 outcomes left, 1, 3, or 5, and we were trying to figure out what's the chance it was a 1. We could also do something like this. I could say, what's the probability that my outcome was 1 given that the roll was even, right? Now in that case, it's even weirder, right? We know that that's got a zero chance of happening. If it was an even number, odd numbers aren't even, right? So a 1, which is an odd number, isn't an even number. If you knew I rolled an even number, you know the chance of me getting that 1 would be 0. So this idea of prior information to help us understand these probabilities is a powerful one. If you know some extra information, you can usually use it to your advantage to modify or update your probabilities to give you more certainty in what is coming out. So how do we end up doing this? Let's go ahead and define it. So the definition of conditional probabilities, conditional probability using a mathematical syntax or a mathematical notation. We'll do it this way. The probability of event A given event B has occurred is equal to the probability that A and B occurred, right? So this is just a reminder, is just the shorthand notation for A intersect B. And then we're going to divide it by the probability of B. And notice here the probability of B, because we're conditioning on that, right? Because we said it happened, that probability has to be greater than 0. That's going to help us avoid that sort of inconvenient or not terribly useful condition of having something divided by 0. If we go back to what we had talked about before, that six-sided die kind of experiment, I could do a little bit of Venn diagramming on that guy. I could go ahead and draw my six-sided die experiment, right? And I could show where all those pieces are. So I could show my sample space. Sample space is what? Mutually exclusive, collectively exhaustive, and finest grain. So I have a 1, 2, 3, 4, 5, 6. And each one of those guys is a 1/6 probability. So if I wanted the probability, right, that I equals 1, given, right, that the roll was odd, right, something like that. What is that? That is the probability that I equals 1 ANDed with the roll as being odd, something along those lines, over the probability that the roll was odd, something along those lines. So let's go ahead and think about how we might compute this guy out. Let's deal with the denominator first. The probability that the roll was odd, we can see that here pretty quick, right? Over here, that first row in there is all the odd rolls. The second one is all the even rolls, right? There's an equal number of elements in each, so I know the probability that the roll was odd is going to be a half. What is the probability that I had a 1 intersected with an odd roll? 1 is a subset of the odd roll. So I equaling 1 intersected with odd roll is just probability that I equals 1. And so what's the chance that I had I equaling 1? That's the thing I'm showing here in dotted. So I can think of that as I equaling 1 intersected with odd roll, right? Because I equaling 1 is a subset of odd. The whole thing just ends up giving me the I equals 1. What's the probability that I equals 1? And that's a 1/6. If I go ahead and do that calculation, I'm going to get a 1/6 divided by a half. And if I do that, I can multiply top and bottom by the reciprocal of a half. So I'm going to have 1/6, right, times 2 over 1/2 times 2. Those guys on the denominator cancel. And I'm left with 1/3, which is exactly what we had before. So we can see that this definition works out pretty well. There are, because conditional probabilities are valid probabilities, there's a whole series of axiom-like properties that we can associate with these conditional probabilities. The book goes ahead and shows this as another theorem. So if you follow along the book, there is this theorem 1.7, if you will. And really, this is just the axioms applied, right? These are the axioms applied to conditional probability. Okay, so what do these things look like? They look a little bit like this. We know the first axiom was what? The probabilities couldn't be negative. Applied to conditional probabilities, it looks something like this. Probability of A given B still can't be negative, right? So we know a conditional probability being a probability can't have a negative value. Axiom 2, if you remember Axiom 2 for the generic case, said the probability of our universe was equal to 1. In the case for conditionals, it looks something like this. The probability of B given B. If I know B happened, what's the chance of B happened? Well, it's going to be equal to 100%, right? Because our universe now is essentially B. So this Axiom 2 for conditional probabilities is really just connected to our Axiom 2 for our regular probabilities that we looked at before. Axiom 3, we know that had something to do with unioning up a bunch of mutually exclusive events. So I might start it out in this way. If A1, let's do it a little different. Let's say if A is equal to A1, union A2, union going on forever, and that the AI intersect AJ is equal to the empty set for I not equaling to J. What does that say? It says the A's, right? This basically here says that the A's, the AIs, are what? Mutually exclusive. They're mutually exclusive. Okay, so I have an arbitrary event A made up of a union of a bunch of mutually exclusive stuff, right? Then is applied to this idea of conditional probabilities. The probability of that event A conditioned on B, right? It's just the probability of the first piece AI conditioned on B plus, and you keep doing that forever. So maybe I put one more in here just to make sure we're seeing the pattern here. So we'd add PA1 given B plus PA2 given B plus, and going on forever. If I was going to use a more kind of compact notation, I could do this as a summation I equaling 1 out to infinity. The probability AI intersect B. That whole thing gives me probability of A given B. Something like that. I think I said that wrong. So probability of A conditioned on B is a summation 1 to infinity of probability AI given B. Something along those lines. Okay, so let's take a look at maybe a very simple application of this one as well. There's a couple ones that we could certainly do on this, but I think I'm going to try to do a couple that are easy to graph or easy to visualize, or where we have a nice way of visualizing them. So let's consider the following experiment. So as an experiment, let's roll 2 fair 4-sided die. Something like that, okay? And I would like to define an event A is equal to at least one die shows a 1, something along those lines. So if I were going to think about this experiment and I wanted to do something like, what is the probability of A? Roll 2 fair 4-sided die, right? And then what's the chance that you have at least one showing up in there? That probability of A, we can get it in lots of different ways. I'm going to start with a picture, right? I'm going to think of the outcomes of the first die. That's a 1, 2, 3, 4. For each one of those outcomes, the other die could also have a 1, 2, 3, or 4. Something like that. And I'm going to show all the possibilities of those outcomes as little dots, something like this. So every single one of those dots, right, is representative of one of the outcomes of this experiment of rolling 2 4-sided die, right? So this one on the horizontal, I'm going to be as being die 1. The one on the vertical is die 2. If I rolled a 1 and a 3, for example, right, the first die was a 1 and the second die was a 3, that would be that guy right there as an example, right? So there's how many different opportunities or how many different outcomes in here. We can see from this that there are, right, we can see that there are 16 possible outcomes. Every single one of them is equally likely. So I know that each one of those dots, right, the probability here is equal to 1/16, right? And it here, and it here, and it here. Every single one of those guys has got a 1/16. What's the total probability? The probability of my universe, right, is a sum 1 to 16 of the individual probabilities. Those are each 1/16. So I'm going to get 16 times 1/16 is equal to 1, as we'd hope. Everything needs to sum up to a total value of 1. So what's the probability that at least one is showing? Let's just highlight anything that has a 1, right? So if die 1 is a 1, any one of those 4 outcomes on die 2 would still result in a 1 being shown, right? If I rolled my first die as a 1, well, then I have at least 1 showing up. Same thing with die 2. Any one of those guys, any of those 4 guys, would also give me this overall idea of having a 1. Now, there's no other dots in there that would have at least 1 in there. What's the probability then? Well, we can see that there is a total of 7 out of 16, right, outcomes, each equally likely, that would end up giving us that 1 possibility out of rolling those 2 dice. Okay, so there's that guy without having any prior knowledge, something along those lines. It's just a little under 50% likelihood, right, that you would have at least 1 showing up when you roll 2 4-sided die. Suppose I modified it just a little bit. Let's say the following. Let's look at what's the probability of A. That's one of those ones showing up, given that both rows were odd. So I don't know with that condition exactly what they were, but I know they were each odd. Now we've changed things, right? When we know that both rows were odd, I know that now all of these guys couldn't have happened. So get rid of all the 2s, get rid of all the 4s on the first dice, get rid of all the 2s, get rid of all the 4s on the second die. And what does that leave us with? That leaves us with things where things are both odd, right? We see that there's only 4 in those cases. And the cases here that have a 1, right, showing up are going to be the ones that I'm going to kind of double shade in here. We see that there's 3 of them. So 3 out of 4 seem to be doing that. So we could get an idea here just by our picture that this guy should be 3/4. Let's see if we can use our definition of conditional probability to get the exact same thing. So what's the probability of A given both are odd? Right? We know that that is the probability of A intersected with both odd, okay? And then we're going to divide by the probability that both are odd, something along those lines. Well, let's first look at the case of them both being odd. What's the probability that they're both odd? If we look back at this diagram, we see those 4 circles, those 4 cases, those 4 outcomes where both die, right, have an odd number. I found that by getting rid of all the even possible ones. So I know 4 out of 16, right, result. 4 out of 16 of those equally likely events are such that both die have an odd number showing. So 4 out of 16 is going to be my denominator. 4 out of 16. How about the numerator? What's the probability that we have a 1 showing, right? And they are both odd. If I go back up there and I do that, I'm going to do this in blue. So I need the probability that they're a 1 showing and that they were both odd. Well, a 1 and a 3 has a 1 showing and they were both odd. A 1 and a 1 has a 1 showing and they were both odd. And a 1 and a 3 has a 1 showing and they were both odd. Those are the only 3 out of the 16 possibilities that could have had that. So in this case, we would have had 3 over 16. Turns out the 16s cancel and I'm ending up with 3/4, which matched exactly what we had seen when we first sketched this guy out. So conditional probabilities. Conditional probabilities allow us to adjust our understanding of likelihood or probability based on some event having occurred or some additional information being known. Usually that additional information allows us to be more precise in our knowledge of what's likely to happen. We usually can use that additional information to our advantage in order to better understand the likelihood of things going on. Okay, so let's look at another example that would show this conditional probability going on. This one's a little different. It's probably not so realistic in its numbers given today's age, but we'll still try it. Let's say that there's a particular population. So the population that we're going to be looking at in this particular case, maybe you go to some particular country and it has this population, or you go to a state and it has this population. We're going to look at a population of 1 times 10 to the 6th people. So 1 million people in this particular population. In that population, the number with phones, okay, is going to be equal to, let's do 1 times 10 to the 4th. So that's going to be 10,000. So that's the unrealistic part here, right? This is kind of a backwards group of people. They don't have a lot of phones in this particular case. Let's also say that the number of people that are called per day, right, is equal like 1 times 10 to the 3rd. So 1,000 people are called on any given day. We can start doing some calculation of probabilities on this, and I think we'll also be able to use our calculations there to show or demonstrate how conditioning helps us maybe modify or update our probabilities and get a better or clearer picture. So what's the probability that any person gets a call, right? that a person gets a call. The probability that a person is given a call is going to be the number of people called, right? 10 to the 3 over the population, total number of people, 10 to the 6th, and that ends up giving us a 1 in 1,000 shot. So for the entire population here, on any given day, 1 in 1,000 is going to get a telephone call, right? Well, here's maybe a more useful one. We could say, what's the probability that you're going to get a call given that you have a phone, as an example, right? That sort of seems a little bit obvious, but that conditioning now, right, is going to reduce part of the probabilities that we're looking at, right? Because only 10,000 people have that phone. How do I get that? I'm going to look at what's the probability that I get a call and I had a phone, right? So we would say maybe probability of a call and a phone over the probability of a phone, something along those lines. And what do we get? Probability of a call and a phone, well, that is 1 in 1,000. What's the probability of having that phone? Well, we had a population of 10 to the 6th, a million, right? 10,000 had a phone. So the probability of having a phone is 10,000 over a million. That's 1 in 100, 1 in 100, something like that. So the conditional probability, the probability that you get a call if you had a phone, is 1 in 10. Now, we could probably get that a different way, right? We could have gotten that a slightly different way just by saying, hey, we knew that there were 1,000 people called a day, right? And only 10,000 people had a phone. We know that getting a call requires you to have a phone. So the probability of getting a call, given that you had a phone, is going to be this chance of getting a call over, just the population that has the phone. So 1,000 over 10,000, or 1 in 10, something along those lines. All of these can be computed out with these ideas that we've been just covering on conditional probabilities. So us conditioning, right? Going away from the general population to the population that just has the phone dramatically changed that probability that we would have looked at. One was pretty unlikely, 1 in 1,000. The other one was pretty likely, 1 in 10, something along those lines. There's another consequence of these things that we can use. We had previously a Theorem 1.9 that we had looked at. What was Theorem 1.9? So a recall. I'm going to just look at a recall. Recall Theorem 1.9. 1.9 says that we had an event space, right? We had an event space, and we did that as B1 going all the way out to maybe some B, I think we called it M, and then we had some event A, right? And we did something like this. We said the probability of A was equal to the summation I equaling 1 to M of the probability of what? A intersect the BI. So that was one of the theorems that we had. We can make an adjustment on this. We can modify that. We can modify that guy with our conditional probabilities, right? What do we know from conditional probabilities? I know stuff like probability, right, of something like A given BI is equal to the probability of A intersected with BI over the probability of BI. This Theorem 1.9 uses this intersect probability, right? What I would like to do is I'd like to replace it with an equivalent to that intersect probability that uses conditional probabilities. So if I just take this denominator, move it to the other side, I can solve for that probability A intersect BI. So I know probability of A intersect BI is equal to probability A given BI times the probability of BI. And then I can take that guy and put it up into there. This gives us an alternate way of finding the probability of A. This particular one is often termed the law of total probability. So let's go ahead and write it out. Law of total probability. This law of total probability. And the law of total probability says something like this. We have an event space B1 all the way through some BM, and we have probabilities of the BIs being greater than 0. So let's let them be able to be happening, right? That's going to be for I going across that whole set. up to m, right? And some event A. In this case, we can say the probability of A equals a summation, I equaling 1 to m, of probability A given BI times the probability of BI. Okay, so that is our law of total probability as modified or adjusted as a consequence of our understanding of conditional probabilities. This one is maybe a little interesting. You might wonder why it is that we would give that when we had something so closely connected before that we looked at Theorem 1.9. That guy right there. We know they have the same origins, the same roots. Why would we be interested in something like this? Well, part of the reason is that in a lot of type of problem statements, you might naturally know or more naturally know things like the probability of A given BI, right? Those might be the givens of your problem. And rather than having to go through all the backwards, computations to connect it to what would be necessary for Theorem 1.9, you can just use them directly here in this law of total probability. There's one more that we can do, and this one is probably something you've heard about before, or at least you've heard the person's name before. There is one that is called Bayes' theorem. Bayes' theorem really is a way of us converting between conditioning on one thing to conditioning on another thing. So it looks something like this. The probability of B given A is going to be equal to the probability of A given B times the probability of B over the probability of A. So how might we use this? If I was given something like a probability of A given B, and I knew likelihoods of both A and B, I could then determine or compute out the probability of not A given B, but of B given A. We'll have a really nice example here in a few minutes to go ahead and demonstrate how this might be used. How can I prove this guy? Let me go ahead and take the denominator on one side and bring it over to the other side. So that is a probability of B given A times probability of A being equal to probability of A given B times the probability of B. But if I go back to my definition of conditional probabilities, I recognize this thing over here, right, as being what? This is probability of A and B, and this other one is probability of A and B. Clearly, those two guys are equal. We're done on that. So really something quite straightforward as far as being able to demonstrate Bayes' rules. Okay, so let's finish out this lecture with a final example that uses some of these conditional probabilities, uses things like Bayes' theorem, and it provides a result that I think most of you will find rather surprising. So here's an example that we are going to do from communications theory. We're going to take a look at a binary asymmetric, it's called the binary asymmetric communication channel. This communication channel is responsible for sending digital data. During that transmission process, there's a chance that the bits get corrupted and they would be received as the opposite bit of what we had intended. That would be a bit error. And we would like to get some models of this guy. I'm going to go ahead and try to draw this with a picture because I think these pictures will help. So I'm going to think about the transmit side. So transmit side. I'm going to do over here on the left. And then I'm going to think of the receive side over on the right. So I'm going to have the transmit side and the receive side of my communication channel. What can I transmit? I know that I can transmit a 1 or I can transmit a 0. So that's going to be my transmission. If I wanted to think about transmitting, let's go ahead and think of that transmit side or the transmit bit as, let's use the letter X for transmit, right? So we could be thinking about we are going to be transmitting a 1. That would be like an X1, or we are transmitting a 0. That would be something like an X0. So this is like an X1 and an X0, something like that, transmitting a 1 or transmitting a 0. On the received side, we could either get a 1 and we could also get a 0. It's going to be classified. It's going to make its best guess as to what's the binary data there. So let's let the received side be designated with the letter R. So this is a receive of a 1 and this is a receive of a 0. Something like that. We're getting started in our picture of this. Let's just hook up a couple pieces in here. The binary. What does that binary mean? Well, it just means that I've got ones and zeros, right? I've got ones and zeros. So this is a binary communication channel. We're only transmitting things ones or zeros. What's the communication part of this guy? Well, that's going to be going from the transmit side to the receive side. So I'm going to have to draw some connections in here. The asymmetric we'll deal with here in just a second. Let's get the communication part. A 1 could be transmitted and it could come through as being received as a 1, right? So that is a case where a transmit 1 becomes a received 1. We could also have a transmitted 0 become a received 0. This would look pretty good if I could just stop there. If it went this way, all ones would come out as ones and all zeros would come out as zeros, and I would have a perfect communication channel. No errors, no noise would distort this guy. We would never get a misclassified bit. Normal communication channels don't work this way. In the real world, there is noise, and sometimes ones seem to come through as a 0 or zeros come through ones. So we're going to have some cross paths in here. We're going to have a cross path where a 0 could be coming as a 1, and we could have a 1 becoming a 0. So I'm going to go ahead and draw those cross paths in there as well. Okay, so we're getting a start in here. What's the asymmetric part? That asymmetric part says something about what's the likelihood of the error, right? The likelihood of the error means something about what's the likelihood that I am going to be making a 1 equal to a 0 or a 0 equaling to a 1, vice versa. So I'm on one of those two red paths that I'm showing in there. If it's an asymmetric channel, those probabilities are not going to be equal. Maybe the chance of making an error from a 1, right, being transmitted is different than the error probability of a 0 on the transmit side. Okay, so the way we can complete this guy out is we can start putting some probabilities in here as well. So I'm going to go ahead and I'm just going to make these in a blue, right? I'm going to do something like the following. The probability that I transmit a 1, I'm going to let as being 50%. And the probability that I transmit a 0 is also going to be 50%. I'm just going to assume it's random binary data, and it's equally likely that I send a 1 or a 0. Now, the next part I might have in here would be something like this. What's the probability, right, that what happens? That I receive a 1 given that I transmitted a 1. That's the path that I'm on, right? It originated from this blue dot that I'm showing here, which says that already I'm looking at the case when I transmitted a 1, which is why I'm doing that conditioned on transmitting a 1. The way we naturally think about this communication channel is going to be naturally described in terms of conditional probabilities. So I'm going to say that when I send a 1, it's going to come out and it's going to be received as a 1 90% of the time. So I'm going to go ahead and let that be equal to 90%. What does that tell you about the chance that a 1 becomes a 0, that 1 is misclassified and received as a 0? Because there's only two ways of getting out of that 1, right? One of them is 90%. The other way is the other side. This is the probability that I receive a 0 given I transmitted a 1, and that's going to be equal to 10%, something along those lines, right? Anything coming out of that branching out node is going to have to sum to 1, something along those lines. I'm going to let the probability that a received 0 occurred given that I transmitted a 0. So in other words, that a transmitted 0 was received correctly is going to be 80% of the time. And that would mean that my probability of receiving a 1 given I transmitted a 0 is equal to 0.2. This asymmetric part, right? This asymmetric part comes out of the fact that the probability that I receive a 0 given I transmitted a 1 does not equal the probability that I received a 1 given I transmitted a 0, and that other associated probabilities. These two channels are not balanced, right? The likelihood of things coming through correct or not is dependent on whether I sent a 1 or a 0. Okay, so I've drawn a picture now. I've drawn a picture that tries to reflect some realistic communication system. And by the way, this does happen. We do get asymmetric communication channels all the time. So it is absolutely possible that a transmission of a 1 behaves differently than a transmission of a 0. So here's the question that I'm going to ask. I'm going to go ahead and put this back into black. So here's the question, right? The question is the following. What is more likely? What is more likely? A received 0 is correct, call that condition A, or that B, a received 1 is correct. So let's go back to where we can see this whole channel and think about this question. I have equal likelihood of sending a 1 or a 0. They go down a communication path. Sometimes the 1s come through as 1s. Sometimes the 1s comes through as a 0. Same thing for the 0. Sometimes the 0 comes through as a 0, and sometimes the 0 comes through as a 1. When I start with a 1, right, it comes out a 1 90% of the time. When I start as a 0, it comes through as a 0 80% of the time. And the question is, what is more likely, that a received 0 is correct or a received 1 is correct? Go ahead and take 2 seconds and just decide for yourself which one is more correct, A or B. If your guess is like the majority, the vast majority of guesses that I get during a normal kind of in-class presentation of this material, what people do is they take a look at this fact that we get 90%, which is greater than that 80%, and so they want to say something about received 1 as being more correct, and they will guess this. So they will guess that that received 1 is correct as being a more likely event. What I would like to do is I'd like to be a little more methodical on this, and I would like to try to make some calculations. So what is this statement that a received 1 is correct? What are we looking at? I think I need to get a mathematical description of condition A and of condition B. Mathematically, what is A? Mathematically says, what is the probability, right, the likelihood, the probability that a received 0 is correct. So what is given here? What is given is that I received a 0. So I'm looking for the probability of something given that I received a 0. Now, for that received 0 to be correct, I must have transmitted a 0. So I'm looking for a probability of transmitting a 0 given that I received a 0. That is the probability reflective of A. On the B part, I'm asking what's the probability that a received 1 is correct. So I'm already telling you that I received a 1, right? So the given here is the received 1. And for it to be correct, I must have transmitted a 1. These are the two probabilities that I'm looking at. Now, if I was going to maybe make this a little bit better, I would do something like this. I'd put the probability x1 given r1 here and go ahead and put my b out there. And then I'm putting a big question mark here and I'm saying, is it less than or is it greater than? Something like that. That's what I would like to figure out. Is probability x0 given r0 greater than or less than probability of x1 given r1? Go back up here. These probabilities that people oftentimes look at in order to guess here is not the probability of x given r. They're the probabilities of r given x, right? So we were given kind of the opposite conditioning than what was asked for. We were asked for something x given something r, right? Whereas the diagram, the thing that naturally came out of the problem statement, was something r given something x, right? So point number one that I would say on this, what makes a lot of these problems a little bit challenging is taking the English language description and being able to come up with what is meant mathematically. Pictures can help, doing an accounting of data can help, experience can help, but in the end we have to be exceedingly careful in making sure we read these problems correctly. The problem here says, is a received 0 correct? The mathematical translation of that is that we are conditioning on having received a 0. That's what was given, and we want to know if it's correct. That would say what was the probability that we transmitted a 0. Okay, since we were given, and I'm going to do this in a highlight of yellow, right? Since we were given probabilities that were not the ones that we wanted, we could go back up here to Bayes, right? If I had something that was in the order I didn't need and I needed it in the opposite order, I should be able to get it through Bayes' theorem, right? So I am going to come down here and think of these probabilities that I need in terms of Bayes' theorem. So what is it in terms of Bayes' theorem? If I look at A, probability of x given x0, probability that I transmitted is 0, given that I receive 0, that's a probability that I receive 0 is correct, is the probability, right, of a received 0 given a transmitted 0, right? Go back up to Bayes, and what do I get on that Bayes? Whatever I was conditioning on in the numerator is the probability that I'm multiplying in the numerator. So I come back down here. So this is going to times the probability of x0 over then the probability of r0. For us right now, I can see a couple of these from my diagram. Probability of r0 given x0. R0 given x0. That's 80%, right? So I know this one is 0.8. Probability that I transmitted as 0 is 0.5. The probability that I received as 0 is still not known. So I need to figure out that. On the other one, the B, that's the probability that I transmitted 1 given that I received a 1. That's going to be the probability that I received a 1 given I transmitted a 1 times the probability that I transmitted a 1 over the probability that I received a 1. This top one is 0.9, this one here is 0.5, and that probability of receiving a 1 is as yet unknown. So to solve either one of these, I'm either going to have to get probability R0 or probability R1, and one is just the complement of the other. Probability of R0 is the probability, right, of R1 complement, which is equal to 1 minus the probability of R1. So if I can figure out probability of R1, I can get all the information I need. So let's do probability of R1. What is the probability that I received 1, and how can I get it? If I go back up again to the law of total probability, which we introduced, what does this say? Some event of interest we can get in terms of its conditional probabilities and conditioned on things like transmitting and the likelihood of those. So I'm going to just apply this using the law of total probability. So I'm going to be able to find my probability of R1 as being equal to probability of R1 given X1 times the probability of X1 plus the probability of R1 given X0 times the probability of X0. That's the law of total probability coming into play on this. If I go ahead and plug these guys in, that's a 0.9 times 0.5 plus 0.2 times 0.5. And if I do all of that, I get 0.55. The probability of R0 then is 1 minus the probability of R1, which is equal to 0.45. As a result, what do I get? Probability of X1 given R1 is equal to probability, we'd already written this down, R1 given X1 times the probability of X1 over probability R1. This is equal to 0.9 times 0.5 over 0.55, which if I calculate that out is 0.818 with a bunch of other digits. That was my condition, right? P of X1 given R1, that was my B. That was my B probability. My A probability was the probability of X0 given R0, and that was probability of, we have R0 given X0 times probability X0 over probability R0. Do all the substitutions in there. That's 0.8 times 0.5 over 0.45 in this case. And if I do that calculation, I get 0.889 and change. What we see here is that A, probability X0 given R0, That was my A condition, right? What was this? That was that a received 0 was correct, right? That the probability of received 0 as being correct was just under 90%, right? And that was greater than the 0.818, which was the probability of x1 given r1, and that was that a received 1 was correct. One of the reasons I really like this example is because we can look at it from where we started. We can get a picture to reflect this communication channel. The kind of probabilities that naturally come in there are stuff that are easy to measure. They're kind of the natural way we would measure them. And the question we asked is certainly a question that could be of interest. And it turns out to be a little different than what was given in the picture. It required some calculation. And the result almost always, when I first saw this problem, I was surprised. I had to go back and double check it twice because I wanted to make it that received 1 was more likely correct. And it just isn't true. It's not true when we go through the math and check it out. This is starting to get to be a long lecture. We'll go ahead and stop here and pick up on the idea of independence next time.